Let us see in this lecture the applications of Biot-Savart's law. That is, first we are going to find the magnetic field due to a straight current carrying wire. Here I'm just mentioning the formulas. The derivation is not required. How you use the formulas, that is more important in the exam. More of application questions are asked in the exam. So I'll just mention the formula. Let us say we have a wire. I need to find the magnetic field at this point P. Magnetic field due to current carrying wire. If you remember in electrostatics, we had calculated electric field due to long wire, infinite wire using Gauss's law. Similarly, we can find magnetic field due to long wire using Ampere's circuital law, but here I'm mentioning for finite wire also. So let us say we want to calculate magnetic field at this point P, and this wire is carrying current. So what is the first step that I need to do is drop a perpendicular from P onto the wire. Keep this point in mind. What is the first step? I need to drop a perpendicular from P, where I'm calculating the magnetic field, onto the wire, and I'll call that perpendicular distance as say R. And then what we have to do is from this P, I'll join a line to one end of the wire, and I'll call this angle subtended as alpha. And from this P, I'll join a line to other end of the wire, and I'll call that angle subtended as beta. Alpha, you have to understand that alpha, you can see that this is a reference line. R vector is the reference line. So alpha is measured in which sense? It is measured in clockwise sense, while beta is measured in the downward direction, that is anti-clockwise sense. So alpha is measured in the clockwise sense, whereas beta is measured in which sense? Anti-clockwise sense. And then the magnetic field at P, this is given by the formula mu naught I divided by 4 pi R. Remember, this R is nothing but the perpendicular distance from the point P onto the wire. I'll write R perpendicular into sine alpha plus sine beta. This is a very important formula. Magnetic field due to a wire, finite wire, we can tell, is given by mu naught I by 4 pi R perpendicular sine alpha plus sine beta. Now, if the wire is infinite, I can come to some cases. Like suppose, for example, if the wire is infinite, let us say we have a wire, long wire. Let us say this is the wire, it is going up till infinity. I need to find magnetic field at this point P. So what is my first step? I will join a line. I'll drop a perpendicular from this P onto the wire perpendicular distance, and I can call that as R perpendicular. From this P, I'll try to join a line, correct, to one end of the wire. So if you see that the wire is going up till infinity, isn't it? This is alpha. So if the wire is going up till infinity, then what will happen? Then this line, isn't it? The line which you're joining from P to one end of the wire, that line and this wire are approximately what? These two are parallel, isn't it? So if the wire is going up till infinity, this line, correct? This line is almost straight, correct? So this angle can be considered as 90 degree because it's almost straight. We don't know where is this wire going up till. This wire is going up till infinity. So from this P, if you're trying to join a line to one end of the wire, this angle will be approximately equal to 90 because that line will almost be straight. Therefore, that alpha will be equal to 90 degree. Similarly, similar is the case with beta. If the wire is going up till infinity, similarly, this angle is going to be how much? This angle is going to be 90 degree. What is a magnetic field then? What is the magnetic field formula? Therefore, the magnetic field is going to be mu naught I divided by 4 pi into R perpendicular. Sine 90 degree is 1 and sine 90 degree is also 1. Sine alpha plus sine beta. Therefore, this is going to be mu naught I divided by 4 pi R perpendicular into 1 plus 1 will become 2. This is the magnetic field due to an infinite wire. Very, very important. Due to an infinite wire, magnetic field is equal to how much? Mu naught I by 4 pi R perpendicular into 2 due to an infinite wire. Let us say if the wire is semi-infinite. If the wire is what? If the wire is semi-infinite, and the magnetic field is calculated at one end, and magnetic field is calculated at one end. In that case, what will happen? Let us say this is that wire, and one end is going up till infinity. One end is fixed. The other end is going up till infinity. And you're calculating magnetic field at one end. See, at one end, we are calculating the magnetic field. So what will happen? You will drop a perpendicular from P onto the wire, call that perpendicular distance as R, isn't it? And from this point P to one end of the wire, you will join a line and call that angle subtended as alpha, which is measured in the clockwise sense. So that alpha is going to be equal to 90 degree. Then from this point P to at the end of the wire, but that P is lying on one end of the wire. So there is no beta that is formed. Only alpha is there. Alpha is equal to 90 degree. No beta. Beta is equal to 0. Therefore, B is going to be equal to how much? Mu naught I divided by 4 pi r into sine alpha, sine 90 degree 1, sine beta is 0. So therefore, B is going to be equal to mu naught I by 4 pi r into 1. So you can easily understand for semi-infinite wire, it is mu naught I by 4 pi r into 1. But for infinite, it is into 2, because you can consider something like this, that infinite is made up of 2 semi-infinites. That's why it is 2 here, it is 2 here, and it is 1 here. This is for infinite and semi-infinite. Third case, one more is there. Let us say this is that wire, and let us say here you need to calculate the magnetic field at this point. So how will you calculate the magnetic field? What was the first step I told you? You drop a perpendicular from P onto the wire. So what you do, you extend the wire, you drop a perpendicular, you drop a perpendicular. This is the perpendicular distance. R is not any distance. R is the perpendicular distance from P to the wire. So I've dropped a perpendicular, that is R perpendicular. And then from P to one end of the wire, to the top, isn't it? To the top, I'll join a line and I'll call that angle as how much? That angle as alpha. That angle as what? Alpha. And then from that P, from that same point P to other end of the wire, from this point P to other end of the wire, the other end of the wire is here. The top end is at A and the bottom end is at B. The other end is at B. So from P to A, I have joined a line and I have called that angle subtended from that R, that reference line as alpha. And from this P to other end of the wire, isn't it? That angle subtended will be called as beta. But as you can see here clearly, that alpha had to be taken in clockwise sense, beta had to be taken in anti-clockwise sense, isn't it? But here beta and alpha both are taken in the clockwise sense, isn't it? So alpha anyways is clockwise, so that is positive. Alpha is positive, but beta had to be taken in anti-clockwise sense. But since we took it as clockwise, beta is going to be negative, and here sign of negative. So sine of minus theta, how much is sine of minus theta? That is going to be minus sine theta. Therefore, what will happen? Therefore, magnetic field is going to be mu naught I divided by 4 pi r perpendicular into sine alpha. Alpha is still measured in the clockwise sense, but beta had to be measured in the anti-clockwise sense from P to other end of the wire. But since the other end is also lying at the top, so from that reference line, we had to rotate to that line, that is nothing but PB. We had to rotate in which direction? We had to rotate in clockwise. Therefore, that value will be negative. So sine alpha minus sine beta. So these three things you have to understand. Semi-infinite wire, finite wire, and if this is the situation. And one more point is, if the point P lies on the axis of the wire, then what will happen? Let us say I'll just draw one simple diagram here. Let us draw one simple diagram here. And let us say I wanted to calculate the magnetic field on the axis of the wire. I hope you understand the meaning of axial line, isn't it? The axis of the wire, let us say this is the wire, you extend the line, you extend the wire. This is only called as the axial line, isn't it? This line is called axial line. And let us say I want to calculate the magnetic field on the axis of the wire. Fourth point. First is infinite, semi-infinite. Third is if beta is also measured in clockwise sense. Third case. Fourth case is if the point P is lying on the axis of the wire. Then what will you do? According to Biot-Savart's law, correct? According to Biot-Savart's law, what is the angle? What is theta? Theta is nothing but angle between dl vector and r vector. As you can see here, theta was in which direction? Theta was the angle between dl vector and r vector. Let us say, like, suppose for example, if this is the wire, and you had to calculate magnetic field, let us say at this point. So according to Biot-Savart's law, correct, due to this current element, let us say this is the current element and this is the direction dl vector. And from current element to point P, isn't it? From current element to point P, you had to draw a vector, isn't it? Current element to P, you had to draw a vector. That is a position vector of point P with respect to the current element. So from the current element, I'll draw a vector like I had drawn a vector from current element to point P, isn't it? Considering the current element to be at the origin. So considering the current element to be at the origin, I'll draw a vector, isn't it? That vector is nothing but R vector. As you can clearly see here, the dl vector is here and r vector is here. So the angle between the two is nothing but 180 degree. Therefore, magnetic field, if you substitute in this formula, this is going to be mu naught by 4 pi I into dl into sine 180 degree or sine 0 degree, anything. Sine 180 degree or sine 0 degree divided by r square. Sine 180 or sine 0, both are 0. Therefore, magnetic field is going to be 0 on the axial line. That is, if you're trying to calculate the magnetic field on the axis of the wire, then the DL vector and R vector will either be anti-parallel or parallel. So the angle between the two will be equal to 0 or 180 degree. Therefore, the magnetic field also is going to be 0. Let us say we have a wire like this. This is the axis of the wire. And the magnetic field at any point on the axial line is going to be how much? Is going to be 0. This is the fourth point that you need to understand with respect to wires. Next, magnetic field due to an arc carrying current. Let us say we have an arc. First was a straight wire. Now I'll bend the wire. I'll make it an arc like this. Now, due to this arc, how do I calculate the magnetic field? Let us say this wire is carrying current I, and this arc is subtending an angle, say theta at the center, and the radius of this arc is say R, capital R. Then what is the magnetic field at the center? Magnetic field due to an arc carrying current, and magnetic field, where are we calculating? At the center. You need to be very careful. At the center, we are calculating. This magnetic field is given by the formula mu naught I divided by 4 pi R into theta. Into how much? Into theta, and theta has to be in radians. Compulsorily, theta has to be in radians, because SI unit for magnetic field, if you want in Tesla, then theta has to be in what? Theta has to be in radians. This is the magnetic field calculated at the center. We can give some examples like magnetic field, and we are calculating at the center. At the center, magnetic field due to a circular loop, due to a complete loop, due to a circular loop carrying current. Let us say we have a circle, we have a complete circle like this, and due to this circle, we need to calculate the magnetic field at the center. So we can use the arc formula, and this is going to, the whole circle is going to subtend how much angle at the center? 360 degree, which is nothing but 2 pi radians. So use this formula. B is equal to mu naught I divided by 4 pi R. R is the radius, theta is nothing but 2 pi. Pi will cancel, to ones are, to twos are. Therefore, it is going to be how much? It is going to be mu naught I divided by 2R. This is for one turn for n turns. For n turns, if the coil is there, and if the coil is having n turns in that, then the magnetic field is going to be mu naught Ni divided by 2R. You have to just multiply by n. This is a very important formula. This is very, very important. I have the general formula for arc, mu naught I by 4 pi R into theta, isn't it? Now, if you want to calculate the magnetic field due to a complete circular loop at the center, the complete circle is going to subtend an angle 2 pi, 360 degree. Put 2 pi, you'll get mu naught I by 2R. And if there are n turns, it is mu naught Ni by 2R. Similarly, magnetic field due to semicircular loop. And we are calculating where? We are calculating at the center only. Semicircular loop. Let us say we have a semicircle like this, and this is carrying current. So semicircle is going to subtend how much angle, people, at the center? 180 degree, which is nothing but pi radian. Therefore, the magnetic field formula will be mu naught I divided by 4 pi R. I'm using this formula into theta. Theta is pi. Pi will cancel. So you'll get mu naught I by 4R. This is the magnetic field at the center due to a semicircular loop which is carrying current. I can have, let us say, a quadrant, 1/4 of the wire. So magnetic field due to a quarter section of the wire, a quarter wire, isn't it? Due to a quarter arc or something like that, isn't it? So here, if I have a quarter circle, due to a quarter circle, and it is carrying, say, current I, and the radius is R. So this quarter circle is going to subtend how much angle at the center? 90 degree, which is pi by 2. And therefore, the magnetic field formula is going to be mu naught I divided by 4 pi R into theta. Theta is going to be equal to pi by 2. Pi will cancel. You will get mu naught I by 4 2s are 8R. And easily you can find the direction using the right hand clasp rule, isn't it? Like, let us say this is in clockwise direction, isn't it? What is the direction of magnetic field at the center? At the center, what will happen? You just curl the fingers in the rotation of the current, curl the fingers in the direction of the current. The thumb is pointing the direction of current. And in this case, clockwise case, the thumb is pointing inward. So therefore, the magnetic field is going to be inward cross. If the current was in anti-clockwise sense, then the magnetic field would have been outward. This is magnetic field due to current carrying element, arc. First was a straight wire. Then the second application is due to an arc. Third application is due to a circular loop. But in the previous case, we calculated circular loop at the center. But this we are calculating on the axis. We are calculating on the axis. So I'll just draw the diagram. I hope you understand this diagram. The circle is not placed in the plane of the board like this, isn't it? It is placed something like this, isn't it? It is placed something like this. So you can have two directions, isn't it? Let us say, and in order to find the direction of magnetic field, correct? Again, we have to use a common rule, that is right-hand clasp rule. If there is an arc which is carrying current, you please use right-hand clasp rule. Right-hand clasp rule is more easier way to calculate the direction of magnetic field. Let us say this is the radius of the circular loop R, and at a distance X, this is the axis of the wire. This is the axis, isn't it? This is the axis of the wire. At a certain distance X from the center, at this point P, I need to calculate the magnetic field. The magnetic field formula is given by mu naught by 4 pi 2 pi, mu naught by 4 pi 2 pi Ni R square divided by R square plus X square the whole power 3 by 2. This is the magnetic field on the axis. Mu naught by 4 pi 2 pi Ni R square divided by R square plus X square the whole power 3 by 2. If you want, we can cancel this pi. So pi will cancel to 1s are to 2s are. Therefore, this is going to be mu naught Ni R square divided by 2 into R square plus X square the whole power 3 by 2. This is the magnetic field due to a circular loop on the axis. A very, very important formula. Now, how do you find the direction? Direction is very, very important. See, in order to find the direction, you just watch it from here. I told you, right? There's a difference between drawing a circle like this, and there's a difference between drawing a circle like this. The second one is in the plane of the board, correct? But the first one is perpendicular to the plane of the board, isn't it? So in order to find the direction, so current can be in any direction, clockwise or anti-clockwise, doesn't matter. Let me keep here in this direction. And in the second case, let me keep it like this. So what you do, if you're calculating the magnetic field on the axis is the place where we are calculating the magnetic field. So what you do, you become an observer here. You become an observer here, and then you understand, analyze. See, here it is there, isn't it? You just see me, how I am doing. So observe from here, just observe from here. So here the current is in which direction? In the first case, the current is like this, isn't it? The current is like this. So from here, you can also just check it along with me. Here, the current is in which direction? Anti-clockwise direction. For me, from here, isn't it? I have drawn an observer here. So from here, the current is in which direction? The current is in anti-clockwise direction. So anti-clockwise direction. So you curl the fingers of your right hand in this sense, isn't it? In this sense, you curl, isn't it? In this sense, you curl that the thumb will be in this direction. That is, the thumb is towards the right. The thumb is along the axis. Keep in mind that the magnetic field is along the axis, but to the right. So again, we are using right hand thumb rule only. Direction is very important. I'm repeating again. So which rule, from which rule did we get that it is to the right or to the left? That it is by using right hand rule, right hand clasp rule. In the second case, if you want to find the magnetic field, this is in which sense? This is in from here. If you just see as the observer, for you, the current is in which direction? The current is flowing like this, isn't it? The current is flowing in the clockwise sense. So curl the fingers of your right hand in the clockwise sense. This hand is like a coil, isn't it? The circumference is the coil. So curl the fingers in the direction of the rotation of the current. Thumb is towards left, but it is along the axis, isn't it? The magnetic field is no doubt along the axis. Magnetic field is along the axis, but either it will be to the right or it will be to the left, depending upon the direction of current. So in both the cases, magnetic field is in which direction? You first keep in mind, magnetic field is along the axis. All the time, you need not have to draw a diagram, isn't it? No need to just check using the right-hand clasp rule. You just remember, if you can check using right-hand clasp rule, but you have to remember that magnetic field, correct, due to a circular loop on the axis, magnetic field is going to be along the axis only, but either it will be away from the coil or it will be towards the coil. So magnetic field is, in both the cases, is along the axis. Along the axis of a circular coil. Along the axis of a circular coil. In the same diagram, what we can do is, let us say you are calculating magnetic field at the center. Then what will happen? This is on the axis, isn't it? So if I want to calculate magnetic field at the center, can we just calculate? That is, instead of calculating magnetic field at this point P, you're taking this point P and putting it at the center. You're taking this point P and putting it on the center. So if you take that point P and put it on the center, what will become 0? X will become 0 because X is the distance from center to P. But now you're taking that P only and putting it at the center. So distance between center and center will become how much? 0, isn't it? So therefore, at the center, magnetic field, we have to calculate X is 0. Just put X equal to 0 here. What will you get? Mu naught Ni R square divided by 2 into r square the whole power x will become 0. 3 by 2, 2 will cancel. You will get how much? You will get mu naught ni r square divided by 2 into r cube. R square will cancel, one r will remain. Therefore, magnetic field at the center of a circular loop which is carrying current is given by mu naught ni divided by 2r. Mu naught ni divided by how much? 2r, which we saw even in the previous case. If you remember here, magnetic field due to a circular loop at the center. This whole thing was all about the center, but in that case we had done on the axis, and from that we are trying to get a case where we are placing the loop, correct, where we are placing the point at the center, so x will become 0, so we get the same result, mu naught ni divided by 2r. Now, one very important ratio is there, a very important ratio is there from the exam point of view. We need to calculate B center divided by B axis. This ratio is a very important ratio from the exam point of view. B center by B axis for a circular loop. Center, if you see, it is nothing but mu naught Ni by 2R. And on the axis, this is the formula. So if I just substitute here, mu naught Ni R square, and then this 2, correct? This term, if I divide, correct, this will go into the numerator. So be very careful while solving this. 2 into r square plus x square the whole power 3 divided by 2. So if you see here, mu naught ni will cancel, 2 and 2 also will cancel. Therefore, this is going to be r square plus x square the whole power 3 by 2, and r square into r is nothing but r cube, isn't it? Now here, since power 3 by 2 is there, I'll multiply and divide by 2. I'll multiply and divide by what? I'll multiply and divide by 2. So here r cube, I can easily write it as divide by 2 and multiply by 2. And then this can easily be written as r square plus x square divided by r square the whole power 3 by 2. I hope you're understanding, isn't it? This 3 by 2 is there. Here also 3 by 2 is there. I've taken a common 3 by 2 and left out is the square. So r square. So power 3 by 2 is common. R square by r square will become 1. 1 plus x square divided by r square the whole power 3 by 2. This is the ratio of B center by B axis. And it's one of the important ratios for the exam. And this has to be remembered. B center by B axis is 1 plus x squared by r squared the whole power 3 by 2.